This is CPR for question 10 on exam 2. Let us first look at a parallel plate capacitor in free space. When a voltage is applied to this capacitor, with this example, the voltage being applied from the left to the right plate, we can say that the left plate has positive free charge and the right plate has negative free charge. This is because the charges on each plate are not bound to the nucleus and thus allowed to move freely throughout the plates. Now let us look at the electric flux density due to the voltage in this capacitor. We know that the electric flux density is going from the positive plate to the negative plate, and a key fact we must know is that the electric flux density begins on the positive free charge and ends on the negative free charge. In other words, the electric flux density is created by free charge only. To find the electric flux density, we just need to know the amount of charge on the surface of the plate, as well as the surface area, which in this case is the surface charge density in the positive x direction. Now let us look at the electric field due to the voltage in this capacitor. We know that in free space, to find the electric field, it is just the electric flux density divided by the permittivity of free space. When we add a dielectric with a known permittivity, things start to change. Let us look at a dielectric when it is placed within this capacitor. When there's a voltage applied to this capacitor, an initial electric field is created going from the free positive charge to the free negative charge. Once we put a dielectric in between this capacitor, this electric field causes dipoles in each atom inside this dielectric to have a partial positive and a partial negative charge towards the negative plate and the positive plate respectively. However, since this charge is inside an atom, the charge is bound to the nucleus of the atom, and as a result, this charge does not move freely around the dielectric, and this is what we call bound charge. Once summed up, this will cause a partial negative side and a partial positive side inside the dielectric. We can also now say that the dielectric is polarized. Now because there is this separation of charge in this dielectric, we can also say that the dielectric itself creates its own electric field, but now in the opposite direction of the electric field in free space. From this information, we can say that the electric field is different inside the dielectric because of the polarization that it caused by the initial electric field from the capacitor. We can sum this up by saying that the electric field intensity can start on either positive, free or bound charge, and ends on negative, free or bound charge, respectively. We can also note that from earlier that electric flux density is only created by free charge, and since we know that there is only bound charge on a dielectric, adding a dielectric into a capacitor will not affect the electric flux density. We also know that work is 1/2 C squared, and the capacitance for a plate is the permittivity multiplied by the plate area divided by the distance of each plate, and the voltage is the electric field multiplied by the distance between the capacitors. Once we combine all three equations, we get that the energy stored in a parallel plate capacitor is 1/2 epsilon times the electric field intensity squared multiplied by the volume, which in this case is the surface area of one plate multiplied by the length between each capacitor. We can now combine everything we just talked about to solve this problem. We know that since the voltage is applied and then removed, the amount of free charge stays the same in the before and after capacitors. Since we noticed the electric flux densities must be the same everywhere. We then know that the electric field intensities must be different in the dielectric and in the gap. The electric field intensity in the dielectric must be the electric flux density D divided by the permittivity of the dielectric 2 epsilon naught, and the electric field intensity for the gap to be the same electric flux density D divided by the permittivity of free space epsilon naught. We can now plug in our numbers to find the work on the before capacitor. We can see that the before capacitor, there is 1 joule of energy that is equal to 1/2 2 of epsilon naught multiplied by the electric field of the dielectric squared multiplied by the surface area of the capacitor multiplied by 10 to the negative 3 meters. Now, when we look at the after capacitor, we know that there is still 1 joule of energy in the dielectric due to no change being done to the dielectric itself. We also know that the free space would need to contribute 1 joule of energy as well. We can now plug in our values for the free space and the after capacitor and get 1 joule of energy to equal 1/2 epsilon naught multiplied by 2 of the electric field of the dielectric squared multiplied by the surface area of the plate multiplied by d. Once we equal these equations together, we now have 4 epsilon naught of the electric field of the dielectric squared SD equal to epsilon naught electric field of the dielectric squared S times 10 to the negative 3 meters to get D to equal 5 times 10 to the negative 4th meters.